Thursday. Thursday. All right, let's get, wow. Okay, let's get started. Good morning. Okay, so we're going to be looking at section 4.7, the first part of that today. It's got a lot of stuff in here, but nothing really new. We're going to spend 2 days on this. Okay, so in optimization problems, we will apply the things that you have learned in finding max, min, and all that stuff to some problems, some application type problems. Okay, and by the way, this section, starting this point on, will not be on exam 3. Exam 3 will cover everything up to what we did last Friday on the sketching graph part. Okay, so there are actually 4 lessons that we'll cover, including this one, that are not on exam 3. We could have put optimization problems on exam 3, but then we felt that optimization problems and related rates on one exam is a bit excessive, so we decided to hold it off. Okay. All right. Anyway, again, like I said, nothing really new here, just application problems. Let's start with this example. We got a rectangular box. And let's suppose that it has a square base. And there's no lid to it. It's got an open top. And this thing has a volume of 4,000 cubic centimeters. Okay, regular box, square base, no top, and the volume specified to be 4,000 cubic centimeters. What we would like to find here is the dimensions, the length, the width, and the height, so that the box would use the least amount of material. Okay, so it's a very typical optimization problem. We're always trying to find the most or the least, the maximum, the minimum of something. Here we're looking for the smallest amount, the minimum amount of the material that's required to build such a box that has a square base, open top, and a fixed volume of 4,000 cubic centimeters. Okay, so to make this more clear, let's sketch a very rough picture of what's going on here. We got our box, just a very typical rectangular box. The base, we're told that it has a square base. So that means the length and the width are equal. Right? Square base. So it's got the same length, the same width. We don't know what it is. That's part of the things we have to find. So you got to start by giving it a name. Let me call those things X. So both of those things are, I'm going to call that x. And this thing has no top, so we can actually look into it. The last dimension we need to know is the height. We also don't know what the height is. Let's call that y. And what we want to find are these two things, x and y, so that it would cost me the least amount of material, the least amount of money to build this box. One thing we know from the problem description is whatever x and y are, whatever they are, we know the volume of that box has to be 4,000, no matter what x and y are. And we know the volume of a box, length, the width, and height, right? So x squared times y. And that thing has to be 4,000 cubic centimeters, no matter what x and y are. And this is actually one equation that we're going to use later that's very important, that will enable us to solve the problem. Okay, so far we've essentially translated the first sentence of that problem statement. Now let's look at the second statement. This is what we have to do. Find the dimensions so that a box would use the least amount of material. If you think about this, if you're trying to make this box out of, say, a cardboard or something, whatever the material it is, it could be a cardboard, it could be a sheet of metal, whatever it is, if you want to use the least amount of material, then regardless of the material you choose to use, it would mean to minimize the amount of surface area of that box. This box has 5 faces, 4 around and 1 at the bottom. You add all of those together, that's the amount of material that's required. And that's what we're trying to minimize. Okay, does that make sense? Yes? Nod if yes. Shake if no. Okay, do nothing if don't care. Okay, mostly nods. Good, good, good. Okay, let's write the equation of that surface area. We'll call that A here. Like I said, there are 5 faces to this thing. There is a base. The base area is x times x. So that's my base. And then I got 4 sides around it. So 4, and each one of these, if you look at the face that's facing us, the one that's facing us here, it has a length of x and the width of y, or width of x and length of y. So each one of that would have an area of x times y. And this quantity right here, we're calling A, is what we're trying to minimize, make the smallest possible. As small as possible. Okay, the equation I want to work with is that A equation. Let me bring it over here. Also from earlier, that equation I underlined in green, that told us the volume of the box. This is saying find x and y to make this small. This is saying that whatever x and y you find, it has to satisfy that requirement. Now take a look at this equation here. Notice this equation has two variables, two things we don't know, and two things that are always changing, x and y. Before you can do anything to it, we have to get rid of one of them. In principle, it doesn't matter which one you choose to eliminate from that equation. Usually, what you want to do is to eliminate the one that appears least often. If you look at here, x shows up twice, y shows up once. Usually, you want to eliminate the one that appears least often. So let me write that down too. Usually the one that appears least often. But again, in principle, it doesn't really matter which one you choose to eliminate. And that's where this equation comes into play. This relates x and y. If you tell me one of them, I know the other. So from that equation, from the equation x squared y is equal to 4,000, we get that y is equal to 4,000 over x squared. If I choose to get rid of y, the one that appears least often, I want to solve for that quantity in this equation. Now we substitute this into a equation. The a equation is x squared plus 4xy. I know what y is, so it is x squared plus 4x times 4,000 over x squared. Notice y is no longer in the equation here. We've accomplished the goal. We got rid of that y. Everything is now in terms of one variable. Let me rewrite this one. It's equivalent to 16,000 over x. Okay, now we can go ahead and find the least to minimize a. With respect to x. At this point, look back to the last page for just a moment and remind yourself what x is. X is the dimension of that base, the length and the width of that base. Don't lose track of what these things represent. Once we find out what x has to be to make a as small as possible, we can use that equation to find y. We get rid of one of them, find it, and then go back and find the other. Okay, so what do we do from here? We've done this so many times. What do we do from here? Take the derivative. What do we find? Right, the critical numbers. Right, very good. So let's take the derivative. A prime is 2x minus 16,000 over x squared. Okay, make that equal to 0. So we see that 2x is equal to 16,000 over x squared, or x cubed is equal to 8,000. Therefore, x is equal to the cube root of 8,000, and that's 20. And that's my critical number, right? At this point, all we know is that potentially this could be a location where a is minimized. Just that alone doesn't tell us that conclusion yet. We have to check that we do get a minimum a. And at this point, you can use either the first or the second derivative test to check if x is equal to 20 gives minimum surface area A. Okay, one or the other, it doesn't matter. You can take derivative one more time and check the sign of that, or you can use the first derivative test and check the sign left and right of that. It doesn't really matter, so I'll use the first derivative test. Remember, here's where we check for the sign to the left and right of the critical number. We would like this to give us a minimum A, so we would like to see negative before, positive after. Let's see if that happens. Here's A prime. If I choose something less than 20, let's say 1. If I choose 1, 1's a very nice number to use. I can't use 0 because of that, right? There's a problem here. I can use 1, though. If I use 1, I get 2 minus 16,000. That's clearly negative. So decreasing before. Here I can choose, I don't know, 10 million if I want to. That's 20 million minus 16,000 over 10 million squared. That's clearly positive. Decreasing before, increasing after. So that gives us what we want. So x is equal to 20 will minimize the surface area A. Okay, that's half the answer. We want to know the three sides. We know 2 of them. We know x. We have to know the last one, y. But just a little bit up from that point, we have an equation for y. So here we go. Now we know x is equal to 20. X is equal to 20. 20. A little bit earlier, middle of the last, about the third way down from the top of last page, we had the equation y is equal to 4,000 over x squared. Once you know one of them, you know the other automatically. And we get a 10. Okay, so what this means is that we want the box to be 20 by 20 by 10 to minimize the surface area. Box that is 20 by 20 by 10 will have the required volume of 4,000 cubic centimeters and the minimum surface area. And so now, regardless of what material you choose to make this out of, this is the dimension that will make will require the least amount of material, and therefore the least amount of monetary cost, while still have the required amount of volume. Okay? Any question on this one? Good? All right. Now in this next example, we're going to turn the question around. In the one we just did, we specified the volume and then we want to find the least amount of material, least surface area. Let's turn the situation around and say I have a set amount of surface area. So in practice, that would mean you have this much material to use. What would the dimensions have to be, the same configuration here, to give us the largest volume? Right? We turn the situation around. Given the amount of material available, make the largest box possible. What's that? Well, I'm going to write it down. It's something you specify, so let's just look at it. So we're still dealing with box with square base. And no top. By the way, in the last problem, what would change if the box had a top? The surface area. So it would be, this would be a 2, right? If the box had a top, then this, we have to account for the base and the top. Therefore, that would be a 2x squared plus 4xy. But everything you would do is still the same. The A equation would change, and obviously the answer would change. Okay, back to here, box with a square base and no top. Let's say if 12,000 square centimeters of material is available. Find the dimensions of a box, of the box with the largest volume. Okay, everybody see how this problem is different from the last one? They're closely related, but kind of the opposite situation. Last time we had a set volume. We wish to minimize the material used. Now we have a set amount of material, and we want to maximize the volume. This is the more usual situation if you were to build a box, right? If you're selling something and someone orders a material, something you produce, you want to ship it out, and you only have this amount of material available, how do you build the largest possible box? Just like last time, to make this more clear, let's sketch a very simple picture and then use that to help us setting this up. Just like last time, we're still dealing with a square base. So call the base whatever you want, x. Call the height whatever you want, y. The volume of this, let's call that V, capital V for volume. Length with height, right? X squared, y. And we would like to maximize this. Find x and y such that this quantity V will be as large as it can possibly get. However, we can't just choose x and y however we want, right? We have to be constrained by the required material available. Material / surface area Just like last time, we have 5 sides. The base, plus the 4 sides. This time we know what it has to be. We know it is exactly 12,000, no more, no less. I have this much material I want to use, and I want to build a box that's as large as it possibly can be. Okay, so that equation is the same surface equation we had last time. The difference here is that it is no longer an unknown quantity. It is now known, completely known. Okay, just like last time, the equation V, you always want to look at the equation that the quantity you want to maximize or minimize. Look at the equation there. If it has more than one variables in it, one has to go. Normally, you want to eliminate the one that appears least often. If they appear equally often, you usually you want to eliminate the one that shows up in the simplest way possible. X squared is more complicated than y to the first, right? So y shows up in a more simple way. Also, look at this equation here. Y is easier to solve. Solve for from the surface area equation. So let's eliminate y. And once again, in principle, you can choose to eliminate any of these two. There's nothing wrong with eliminating x. Nothing whatsoever. It just makes what you have to do a little bit harder. Okay, I'll write down the two equations we're working with again. Okay, we've decided we want y to go, so we solve for y from here. And we get y is equal to 300 over x minus 1 over 4 times x. Then we take this, sub into that. And then what's going to happen is that v will lose that y, because y is in terms of x now. Regardless of how complicated it may look, now we got rid of one of the variables, and that's more important than how complicated it may look. For right now, we can't deal with more than one variable. You have to wait until 261 to learn how you would deal with multiple variables. Simplify this a little bit, we get, sorry, there's no square here. Okay, so v is 300x minus 1/4 x cubed. Now we do what we did before. You take the derivative, find the critical number, verify that it gives you what you want, and then answer the question. Okay, derivative 300 minus 3 over 4x squared. Make that equal to 0. And we get 300 is equal to 3 over 4x squared. So x squared is equal to 400. Therefore, x is equal to 20, or x is equal to negative 20. That's good. Right, exactly. So always at some point you got to look back to the problem you set up, and you got to remind yourself, what are x and y representing? Remember, in this problem, x is representing the length of the base, one of the sides of the base. So is y, is a length. So these are both critical numbers. However, this one right here, this one doesn't make any sense in the context of our problem. In our problem here, x is representing one of the sides. There's no such thing as a negative length. So that's why we remove that. We ignore that. Can't have negative length. Some physical quantities can be negative, but a lot of them cannot. Length cannot, weight cannot, volume cannot be negative. So this is the only thing remaining. We still have to check that we do get the minimum, the maximum v. Okay? This time, let's use the second derivative test. This time, let's use second derivative test to verify x is equal to 20 maximizes v. Okay, how does that test work? Remember? Right, yeah, exactly. You take the second derivative, plug in your critical number, look at the sign of the second derivative. Let's see, second derivative is negative 3 over 2x. Right? So the second derivative at x is equal to 20 is clearly negative, which means it is concave downward with a flat horizontal tangent line because v prime is 0. So this tells us that x is equal to 20 will maximize v. Okay, again, that's just half the answer. You got to remember physically what you were solving for. You always have an equation somewhere that gives you y once you have x. That's how you got your v to be down to one variable in the first place. So look up on the right side of the last page, about halfway down. From earlier, we got this equation. Y is 300x minus 1/4 x. Put 20 in there. So we get 15 minus, that's 5, right? 10. There we go. same three numbers. Why are they the same? Because I chose the V and A very carefully to make them the same. So, coincidence, right? Coincidence. When I set up the examples, I chose the numbers so that the math works out relatively cleanly and turn out to be the same number. So the question is answered here. If you have 1,200 square centimeters of material available, this is how you want to build your box without a top to it, such that it would have the largest possible volume. If you're shipping this thing, you're going to have to put a top on that. So a more practical question would require a top, and what's going to change would be this one right here. You will need a 2 here, and the answers will change. But without a top, this is how we can build the largest possible box with 1,200 square centimeters of material available. Questions on this example? Nope? Okay, good. I have one more example here. This one's not about a box anymore. There's only so much you can do with boxes, so we're done with boxes. This time we're going to go back to just simple geometry here. What is the minimum distance between the line y is equal to 2x plus 4 and the origin? Okay, a much simpler problem, but actually, as we go through the example, you'll see the math that we have to do actually is a little bit more complicated. We got a line here. Let's sketch this out. These sketches aren't required, but they often help you visualize what you're doing. So here's my line. Here's the origin. Question? Yeah, absolutely, right. So every point on this line has a distance to the origin, right? Every point has a distance. So let's say this point is x comma y. This right here is the distance from some arbitrary point on that line to the origin. And you can see, looking at all the possible points, the point that would be the closest to the origin would be right here. Closest to origin. Now, before doing anything, before doing any math whatsoever, this tells me I'm expecting a negative x and a positive y. That's one way I can check my answer, even without doing any work. From the picture, we know x must be negative, y must be positive at the point closest to origin. If after I've worked all this thing out and I got something that doesn't fit that description, I know I've done something wrong. That cannot possibly be the right answer. If this question were to show up on the exam, knowing this geometry right here could help you eliminate one, maybe two of the 5 choices, depending on which 5 choices you see. Okay, so it's always of some benefit to sketch out the situation you are provided with. Okay, now let's solve the problem. Distance from any arbitrary point xy to the origin, 0, 0, is, we know the distance formula, right? D is equal to x minus 0 squared plus y minus 0 squared. So there's the distance formula. We want this to be the minimum. We want to find x and y such that d is as small as it can get. Just like in the previous 2 examples, one of these 2 has to go. For this one, just use the line equation. The line equation tells you whatever an x and y are, whatever they are, they must satisfy this. In other words, if you tell me what x is, that equation tells me y. So that's what we can use. The line equation says y is equal to 2x plus 4. So we can remove that y by doing this. Okay, the distance equation now only has one variable. The next step should be familiar to us. We find the critical number, check that. Before we take the derivative of this, though, there's one more thing we can do to simplify what we have to do. So I'll write down what's going on here. This d is not easy to differentiate. Because of the radical, right? You got to use chain rule and you got a radical, and then when you take the derivative of that, you'll get something to the power of negative 1/2. And that's going to be a big mess, big messy fraction. That's kind of annoying. So we're going to use the fact here that d is always positive. That distance we're talking about is always positive, right? There's no way we can get a negative distance between that line and the origin. Let me rephrase this. Since d is positive, d squared will have the same value of x. That minimizes it. If something is always positive, the value of x that will minimize that is the same value of x that will minimize the square of it. This is only true if that is positive. Let me write that down. Only true for positive quantity. In other words, this means that we can minimize or maximize, it doesn't matter, d squared instead of d. What's the advantage? The advantage is once you square that thing, that radical goes away. We no longer have to deal with the radical. Okay? The same x for d squared will also minimize d. So let me call d squared f. And now we got rid of our radical. And we can now work with f instead of d, so we no longer have to deal with that radical, right? We still have to use chain rule, but that's really not big a deal, that big a deal. Excuse me, let me close that door. Okay, where were we? Oh, here. Now let's take the derivative. F prime is 2x plus 2, 2x plus 4, right? Times 2, very good. Chain rule, don't forget the chain rule. I brought a 2 down here, kept that, reduced the power by 1. I need another 2 because of the chain rule. Make that equal to 0. Let's solve for that. What do we get? We get 2x plus 2, 2, 2, and that's 8. 4, 8, 32. No, 16, sorry. 2 times 2 times 4, right? Equal to 0. So that means 10x is equal to negative 16. X is equal to negative 16 over 10 equal to negative 8 over 5. Right? Okay, remember earlier we said that we expect x to be a negative number. And we do have a negative number. So this looks like the right number. At least the sign is what it should be. And what's that? Exactly. Now we need y. And as usual from earlier, we should have an equation of y. Where's y? Oh, no. We're given that y equation, 2x plus 4, right? So y is 2 times that thing plus 4. It turns out to be 4 over 5. Trust me. Okay? So point on the line, y is 2x plus 4. Closest to origin is minus 8 over 5, 4 over 5. We're not quite done yet. What did the problem ask me to find? The distance. I found the point, right? I didn't quite answer the question yet. I want to find the distance. But, of course, once you got the point, distance is trivial. The minimum distance, therefore, is x squared plus y squared under a radical. We're working with the real d equation now because that's what I need to find the real distance. D squared simply help me find what x has to be. They would have the same value of x to minimize each of them, but they wouldn't have the same minimum. Okay, once you put this number in, you get radical 16 over 5. Okay, any question? All right, that's it for today. See you Wednesday. depends on the person in charge of the course. It doesn't always. Often it does, not always.
You teach Calc too?
I do.
Oh man, can I have you next semester?
I know.
I need to go do that.
Well, dude, it's on the 20th. We actually can be able to register.
On the 20th?
Yeah, I think
Oh yeah, yeah.
freshmen have to wait a little bit.
Well, Calc 2 is harder than Calc 1, so I'm gonna need you again. I'm gonna need you again for Calc 2. It's gonna be even harder than Calc 1. I've heard the horror stories.
Dude, happens to be my favorite course to teach, actually.
Oh boy.
First question. Okay, so this one's on the fourth exam, correct?
The final exam.
Final exam. But it won't be on this exam.
That's correct. The exam on the 16th will not include this material.
Okay. So is there any other lectures after this that will have
We're
more?
going to cover 4 lessons, including this one, that are not going to be on exam 3.
All right, thank
But
you.
they will all be on the final exam.
I know. Thank you.
Hi, I have a question. So I have extended time and I went to talk to the schedule
Last
time,
roll
yeah,
2, yeah.
and I was wondering because the day of the exams I always have like a 4 second.